I think 6, part 2. We're talking about derivatives as rate of change, and we're finally going to see some application and put some of the stuff we learned in perspective. So we define calculus as a study of evolving systems, of changing systems, and we define derivatives as something that measures the change. It measures the rate of change. So just by writing that f prime of x is dy over dx, you see that it's some kind of a fraction. D stands for change from delta. Now delta y is defined as y2 minus y1, and delta x is defined as x2 minus x1. Those are changes. Change in y and change in x. We also said that we have the slope of the secant line as y2 minus y1 over x2 minus x1 for 2 points x1, x2, x1, y1, x2, y2. And that one can also be written as dy over dx. So something like this will be known as average change. Slope of the secant line. We're talking algebra 1, right? The slope you know from algebra 1. Nothing special, nothing fancy. Example, a volunteer. How far do you live from RVCC in miles? How much? 17 miles. How long does it take you to get to RVCC? In minutes, hopefully not hours. 20 minutes. So with this piece of information, I can visualize the start point, home, and the end point, RVCC, starting at 0 to 17 miles, starting at 0 time, driving 20 minutes is 1/3 of an hour. So now, I will say we know that velocity is distance divided by time. Distance is 17 divided by 1/3 of an hour. 20 minutes is 1/3 of an hour. And we're talking 51 miles per hour average. This includes stop signs, red lights, if those are obeyed, obviously, and speed limits if they're observed. Now I can guess that you live on 78 somewhere, the next directly. So this is the average. The velocity graph for something like, for the trip like this, is not going to be a constant 51. No. It's going to be, if you have velocity here in time, 51 average, we'll see how that goes. But if the average is 51, that means that the person who's giving us these numbers went faster than 51 at some times, because I know that the person sat in a car while car had 0 velocity. When you unlock the car is parked, hopefully, right? You don't jump into the car moving at 50 miles per hour. So at time 0, you are starting with 0 velocity, and then you accelerate, and then you maybe drive on some constant speed, and then you stop on a stop sign at 0 again. No, that's stuff, rolling stops or stuff like that, no. and then after the stop sign you wait at 3 seconds. It's the rule. Then you accelerate again. Maybe you drive now faster, a little bit faster, a little bit faster, right? And then maybe there's a red light, so it falls down. So now you wait even longer. Right, it's a red light. If it's delayed green, then you have to, wait much longer. Eventually you go again, and so on. So the trip might look something like this, and then the average of 51 miles per hour might be right there, which means that's 60, that's 70, right, and so on. So what average does is it averages all of the speeds from the time you leave to the time you get to your location. Now, when you glance at the speedometer, you are looking at the derivative. You are looking at the instantaneous speed, and that's going to be the slope of the tangent line. So that's the derivative. You know how when you are going, let's say, from one point to another, home to RVCC, you take streets and roads? Well, that can be turned into a function over time, and that's going to be position function. And when you take derivative of that, you get the velocity function. And then velocity function, you take derivative of that, you get the acceleration function. And you will see every time when you brake, it's going to be negative number. Every time you speed up, it's a positive number. All of that stuff works. It's one-to-one correspondence to what's actually happening as you're driving. And in some cases, you can get a ticket for instantaneous, and we'll see later in some cases for average as well. So, but no, the tickets are written only for instantaneous speed, but there is something that we're going to talk about later that can hint one from the other. So now we are going to take a look at instantaneous velocity as well. So instantaneous velocity at a point A is going to be the limit, as usual, right? As the change in time goes to 0, and I'll explain that as well, of f of a plus change in time minus f of time divided by change in time, which is also known as the f prime computed at a. That one is instantaneous velocity. Now, all of these calculations you already know. You know how to find derivatives. You know how to plug a value in a function and get a number. We haven't learned any new mathematics. What we're learning now in this section is how to apply formulas and concepts we already know and make them work for us. That's what we're doing now. So let's take a look at an example. So first, something from physics that you have to distinguish. So distance versus displacement. So here's your home. Here's the RVCC. Here's the shop right there. And then back home. So let's say your life consists of this for a day. Get up in the morning, stretch, do some math, go to RVCC, do some more math, and then go to ShopRite, pick up some food, and go right back home to do more math. Now, let's say that home to RVCC is 17 miles, and then there is 1 mile between RVCC and ShopRite, and then 18 miles to go back. So now, what are we talking about here? Well, thinking about the distance covered in your trip. Distance is simply going to be 17 plus 1 plus 18 for 36 miles. So you covered 36 miles if you use the car for all of this, right? The odometer will tick 36 miles, and then you're 36 miles closer to the next oil change. Now, what is the displacement? Displacement is a different creature. Displacement from home to RVCC is clearly 17 miles. Displacement from home to RVCC to ShopRite is clearly 18 miles. Displacement from home to RVCC to ShopRite to home is 0 miles. And this is something that we need to discuss. So, let's take a look. The distance measures your distance covered, which is how far you went. Displacement is positional. If you choose the home to be the center of the world, then anytime you're home, you are exactly 0 miles away from home. So it doesn't matter if you go to vacation to North Pole, visit Santa, and then you come back. The distance is whatever distance you covered, which is how far you went and came back, right? It's a round trip. But the displacement is 0 because you came back home. So displacement is measuring from the reference point. In this case, home is the reference point. So you will find that ShopRite is 18 miles away. Either way you go, through RVCC or directly to ShopRite, ShopRite is 18 miles from home as a distance and as a displacement. Distance from home, RVCC, ShopRite home is 36 miles, but the displacement is 0 because displacement says, how far have I went? Well, if you started at home and you ended up at home, you went nowhere, all right? So the distance is going to measure everything you covered. The displacement shows just how far at the moment you are away from whatever reference point you chose as your reference point for your calculations. So anytime you're measuring anything from home, and if you're at home, the displacement and distance do not agree, because displacement is going to be 0, distance is going to be whatever you covered, and then you eventually came back. All right, so let's go and take a look at an example. So we have an object. Let's go in the homework assignment and take a look at one of the problems. It says, a stone thrown vertically on Mars. So we have a stone that we throw vertically on Mars, and the function, so this is problem 18, and the function that governs the path for the rock is going to be negative 6 t squared plus 64t plus 192. Because it was thrown from 192 feet above the ground, So let's find the velocity of the stone. So velocity is going to be defined as the derivative of position. And derivative of position now is what? Looking at the position function, what is the derivative? Anyone? Plus 64. Very good. So the derivative of t squared is 2t. Negative 6 times 2 is negative 12. So negative 12t plus 64. The derivative of t is 1. Great. So now we can figure out the velocity of the stone at any point. You ask me what's happening at 2 seconds. I just need to plug in 2 and tell you 64 minus 24 is 40. It goes 40 miles per hour. It's as simple as that. Part B says, when does the stone reach the highest point? Well, anything you throw up due to gravity has to come down, right? So that's the rule. So now if you observe this motion, observe how the object goes up and then stops and then goes down. It stops at the highest point because it stopped. It can't reach any further than that because it stopped and then it turned down. Now what's the velocity at the highest point? Zero. Object stopped, right? When you throw something up, it stops. So if you're looking for the highest point, you can find it by simply setting velocity to 0, because at that time, object is at the highest point when velocity is 0. It's guaranteed that object must stop, and then it's going to change the way velocity goes. It's going to go down. So this is at velocity equal to 0. So now I have negative 12t plus 64 is equal to 0, from where 12t is equal to 64, and then we divide. T is equal to 64 divided by 12. We can cancel by 4 and get 16 over 3, I hope, which is about 15.3333 seconds. Sorry, 5.3333 seconds. And then they're asking what is the height. At the highest point. What is the height at the highest point? Well, let's check. You have the position function that checks that. We just need to plug in 16 over 3, because we know that at time 16 over 3 we have the highest height. So 16 over 3 squared plus 64 times 16 over 3, and then that's equal to plus 192. Now to compute this, note that one of the 3's can cancel with 6, so you have 16 squared, which is 256, times 2, which is 512. So we have negative 512 over 3 plus 64 times 16. Well, the fastest way to multiply by 16 is to multiply 4 times by 2. So we have a 64 times 2 is 128, and then 256, 512, 1024. So 1024 over 3 plus 192. It's going to be 512 over 3 plus 192. And what do I have? 5 plus 1 is 6 plus 2 is 8. It's not divided by 3. Nah. So we can multiply 192 by 3 and get, well, that's 600 minus 24. So 512 over 3 plus 600 minus 24 is 76 over 3. Yes?
What's that second value next to negative 512 over 3? It's
1024 over 3.
Oh, that's a 4.
A 4 at the end? Yeah, it's a 4. So 1088 over 3, 8 plus 8. Well, it's not. So it's going to be 1088 feet. So the feet. When does the stone strike the ground? What's the height of the ground? So set the first equation equal to 0. And that's going to happen when S of t is 0. So we have, now this is not the calculus obviously, so minus 60 squared plus 64 t plus 192 is equal to 0, and then we find roots for this one. So first of all, let's see if we can factor at least something. We can definitely factor 2 out, right? Because each number is even. 6 plus 4 is 10, so that's not divisible by 3. On the other side we have 12, that will work. Such is life. So minus 3t squared plus 32t plus half of 90, so it's going to be 96 equals to 0. And now we have to find factors of 96. No, 3 times this. I should ask Mathematica to factor this so we don't have to. Here, another selling point for Mathematica. When you have applied problems, you really don't want to sit there and grind through algebra that you don't have to grind through. So factor negative, let's go with the original equation, negative 6 t squared plus 64 t plus 192. And we get these awesome factors here. So technically solve the first one equal to 0. How about we look for the roots? Or we can also say solve and then set it equal to 0. There you go. So we are looking for the positive root, which is 16 over 3, approximate form, 13.1. So it will take 13.1 seconds for the rock to hit the ground. At what velocity does it hit the ground?
Right before it hits the ground.
We have to calculate in our velocity equation. We have that the velocity calculated at 13.1. And our velocity was that derivative. So negative 12t plus 64. So what do we get? Negative 93.2 feet per second. Is it good to be negative? Is it? It's going down. Yes. We established earlier that we want all of the downward motion to have negatives associated with it because we put the gravity to be negative number. So negative, we use negative 12 over 2 because the formula is negative 1/2 gt squared. Since the gravity is 12 feet per second. By the way, you are almost three times lighter on Mars than here because the gravity, right? The gravity on Earth is 32.2 and the gravity on Mars is 12. 12 times 3 is 36. That's close enough. So you're almost 3 times lighter in terms of pounds. 3 times lighter on Mars. Good. So now you see what we can compute with these. If you have the position function in terms of time, you can differentiate and get velocity. You can differentiate one more time and get the acceleration. And then when you have the velocity, you can set velocity equal to 0 to find the highest point for the object to reach, because the object has to stop and then change the motion and start going down. You can find, so first you will find when that happens, and then if you bring that number into a position function, you can find at what height. And you already found at what time. So, just stop a little bit, think about it. Say, I have a position function which calculates position, right? If you give me a time, I will always be able to calculate position. What is the type of the position that it gives? It gives the position. You throw anything, it's going to fall down. That's the ground. It was thrown from 192. Here's your max height. That's how it goes. So stop for a second. And this is the part where you actually have to sit down and learn. And observe. It's much easier if you observe the actual event happening rather than just trying to learn and memorize for the test, because a problem like this is going to show up. I have a position function. If I differentiate, I get velocity. If I differentiate again, I get acceleration. All of those functions in terms of time. So as soon as the time is provided, I can know how high, I can know how fast, I can know how fast it accelerates. So I know all of those three if I have the three functions: position, velocity, acceleration. I can calculate the highest point, simple, because I can set velocity equal to 0 and then use that time in a position equation to find how high is the stone. What's the maximum height that it will reach? I can calculate when it's going to strike the ground if I set the equation equal to 0, because that's the root. So you find the roots of the function, and then that's when it hits the ground, and then you go from there. So physics has a huge use of this, guys. This governs planetary motion. We still use this to send stuff to space station and to moon. We don't need any more precise mathematics than Newton's laws to send the stuff there. Newton's laws are actually not correct. They're adjusted today through quantum world. We know much more about the world today than what Race knew when Newton was around. Newton's laws are good to approximate the planets, how that moves the orbital, right? The big stuff. It's fine. But actually in the core, each one of those equations does not work as a general rule. So yeah, it's good for cars. Cars are still big, all right? So works of planets and cars and falling rock. How about some business? Let's talk about marginal stuff. We have the average and the marginal cost. We have also average and marginal profit. So in the world of business, we would use calculus concepts, except for some reason the word derivatives is either, I don't know, too hard to say or to spell or something, so we're going to use the word marginal instead, but it's the same thing. It means the derivative. So marginal cost is the same as the derivative of cost, obviously cost function. So let's write the formulas here. Cost function C of x x is number of items. Then we have the average cost, which is noted as C bar for average. And that's the cost function divided by the amount of units produced. And then we have the marginal, which is actually our instantaneous. Marginal cost is going to be the derivative, so C prime of x. So you just take the derivative. So that's the vocabulary. And now we're going to take a look at a cost function to produce X items of, I don't know, early production of Tesla cars. How about that? I don't even know if this is going to make it, but I see that the limit is 1,000, so units. So, example. So the cost function in terms of units produced is given as negative 0.02x squared plus 50x plus 100. That's the cost function, and the number of units produced is between 0 and 1,000. So our production limit capacity is 1,000. Determine the average and marginal cost functions. So part A, we just need to find the functions. Well, you take the cost and divide everywhere by x. We get negative 0.02x plus 50 plus 100 over x. So that's going to be the average cost. And then C prime is the derivative, which is negative 0.04x plus 50. Derivative of 100 is 0. So that's going to be marginal cost function. What happened? Because times 2, right? Derivatives. the derivative of x squared is 2x, so it multiplies the coefficient. Good. Took care of that. Part B. Determine the average and marginal cost for the first 100 units. So, compute part A at x equals 100. Well, let's do that. Average cost for 100 units. How much is the average cost? Well, it's going to be negative 0.02 times 100 plus 50 plus 100 over 100. So 2 zeros, I get negative 2 plus 50 plus 1. It's $49 per unit. So average cost to make whatever we're making, definitely not Tesla cars because this is 49 bucks. So you figure out what you would make about 100 for 49 bucks. Definitely sounds like something for eBay, all right? And then the derivative computed at 100 is going to be negative 0.04 times 100. Oh, wait, I didn't square here. Oh, no, I'm not supposed to square. Plus 50. So this is going to be minus 4 plus 50, $46 per unit. And now the question is, what are these numbers? Trying to figure out, should I explain it now or should I compute the part C and then explain? Man, let's compute part C because we're doing the same thing except at 900. So now what do we have? We have 900 times this, so that's negative 18 plus 50 plus 0.9. No, it is 1/9. And 1/9 is about 0.11. So 50 minus 18 is 32. So 32 and 11 cents. And now we compute the marginal cost, which is the derivative, at 900, negative 0.04 times 900 plus 50. So now we have negative 36 plus 50 is $14 per unit. And now it's time to understand what is happening here. What are these? So I'm going to set the production, put it on a number line here, 0 to 1,000 units produced. When I call this point 900 units, I'm going to call this point over here first 100 units. So now, let's understand this. The average cost tells you how much on average each unit is going to cost when you want to produce whatever amount. So now we know that there is a $49 per unit price if you are only making 100 units. So you will have to know that because you need to know how to price your item. You can't go and spend 50 bucks to make something and then sell it on the market for 23, right? So that's why those companies that deal with certain things like clothing companies, if you look at some of these, they make insane profits because, I mean, technically, how much is the cloth? Not that expensive, right? And how much are kids in Malaysia? Even cheaper, right? So when you put those two together, they make a huge profit, right? The cost is about 18 cents per nothing, and then right per coat, and they sell it for 300. And then even when it goes on a sale for 25 bucks, they still make $24.50 profit on it. You know, technically, there you go. So $49 will cost to make 100, but that's per unit. So technically 100 times 49 bucks on average. And what is the $46? $46 is the price, the cost of making 100th unit. So you see that it is profitable here to keep making units because the $46 says that the 100th unit to be made cost you $46, where on average each unit should cost $49. Obviously, the more you produce, the less it costs. Anything that is custom built or unique is extremely expensive. Like any painting should be very, very expensive because there's only one of a kind. Maybe the artist can make a print and and keep printing the painting, but still there's just going to be one original, one first. So that's why something like that is and should be extremely expensive. Anything that is mass-produced should not be expensive. All right? Should not be expensive at all. And we're talking thousands and thousands of dollars for no reason for our equipment that is value-wise not more than $600. And you look at the hardware and the software that is included. Point made. Now, oh yeah, you caught the Apple reference there, right? Finally, good. Yeah, the garbage that they make is sold for $2,000 per computer, and it's no more than $600 worth. So there you go. Now we're going to go to 900 units sold. 900 units sold says that the price per unit should be $32, right? $32 per unit in cost. And we are looking at a significant reduction from 49 per unit down to 32 per unit. And if you look at the price to create the 900, it's only 14 bucks. So that tells you that the more you produce, the cost of production goes down. So it is in your interest to produce as much as possible and sell as much as possible. And if you can keep the same price, you will be making large profit. Who is profiting the most? Oil companies. Why? Everyone has to put the gas in their car. We have the cheapest gas in the galaxy. The gas in Europe is 3 times more than here. Anyone anywhere complains in US even when it was $5 per gallon? When it was 7 in Europe, right? Right now it's 7 per gallon in Europe, 7 or 8, right? That's what the price of gas is there. Someone complains over here and says, the $2.50 look insane. No, it's not. It's going to be insane when it's $9. Then I say, yeah, right? As long as it's less than $9, I don't want to hear it. It's insanely cheap. Pharmaceuticals, right? Yeah, we're going to be without our drugs, right? So, mass production of those, right? Keep taking one pill to counter the one you took before, to counter the 2 you took before that, right? And keep doing it. So, as I said, mass production and whatever you sell a lot of, there's a lot of profit to be made, and I hope you see these numbers and you understand how it goes. So one more time, the average, which is the C bar, whether it's 100 or 900 units, that tells you on average how much each unit costs. And only when you compare the average to an average, you can see that the price went from $49 per unit for first 100 units down to $32.11 per unit for 900 units produced. So we see that it is in our interest to make more units because it will get the price cost down. And then the marginal cost computes the price for a single item. So we have a C prime of 100. It only computes how much it costs to make that particular item. And that particular item, the 100th item, was $46. And to make a 900 item is $14. And then you can compute for the other ones, right? You can compute for 1,000 if you want. You can compute for any other and see how much it would cost for you to produce any one of those. So that would be the business application of this. As long as you have any kind of equation, the profit, the revenue, the cost, you can put them together. The profit is the money that you are making when all the cost is paid. You have the business, you have to factor in the electricity and the gas and the transportation and renting the facilities or a warehouse if you need to, and also salaries and insurance, and all of that stuff is the part of the cost. So when you start working for a company, you are receiving a salary, which is the money you use to buy food and survive. For the company, it is a cost. It is a cost to pay you, right? So how they cut the cost? Layoffs, right? And so on. If they automate certain part of their production and they don't need people, obviously it's a layoff. So that's all of the part of the cost. And then the revenue is all of the money that you make by selling a product. So let's say whatever this is, if you're selling $100 per unit, right? $100 per unit, that means, and the 32 was the average production cost, then 32 times the amount of units, and then 100 times the number of units sold. So let's say you sell all 900. The profit is going to be revenue minus the cost. And then the profit is what you use for research development, right? To make your product better, to hire, better people, to get the better machines, to even increase more production, and so on. So that's how it goes. Successful businesses have this analysis done, detailed, and so on. And a lot of people don't understand this. Their private businesses might fail quickly, because if they don't know how to leverage this to figure out whether their profit is there at all or not, or they can hire people to do that for them. Where one of the favorite things to, I heard this, I can't remember where I heard this, but I heard this maybe 5 years ago. It says, "Oh, you know nothing about mathematics? Can I be your accountant?" Right? It's kind of a menacing statement, but it's true. I mean, such is life. All right. Great. There's another example in the textbook that you can explore. I think something about pork. Elasticity in pork prices. There you go. So you can take a look at that one as well. And that takes care of the derivatives at rate of change. So why is it called the rate of change? Because, again, the derivative was derived from the difference quotient, and the difference quotient was derived from the simple division, which was the slope of the secant line. We did that in 3.1. Same argument there. So we have the average change and we have the instantaneous change. So always remember, driving a car, if you glance at the speed, the split second that shows what the speed is the instantaneous velocity, and then the speed that you can calculate when you get home from wherever you came from, you know the distance, you know the time, when you divide the two, you get the average velocity. So that's the one that smooths everything out. Another analogy between the two is to look at the, let's say, a photo finish for horse races and a video of a horse race. So you have a video of horses running through the finish line, and then there's going to be a photo finish, which is the photograph of the first horse hitting that, going through the sensor that closes the circuit and says, yep, that's the time, and then the photograph is taken. It is extremely small time to take a photograph. Fractions of a second. Fractions of a second. And that is exactly the part about instantaneous. That fraction of a second is here. Change of time going to 0. We would like to take those photographs in a very, very short interval of time, because we know that if you get to expose the, well, now it's digital, but in the early days, if you're exposing film for a longer time, you get the blurry motion. And you need special cameras to catch extremely fast stuff, those that take pictures very, very quickly. So that's this DT going to 0. And then engineering of that, obviously, is very involved, which is making those cameras extremely, extremely expensive. So instantaneous versus the average, and then you have in business, let's say, there are other applications you can come up with. In business, you have, again, average cost versus marginal cost. The marginal is the instantaneous, so you see that you are producing. So when you're talking about marginal cost, you are talking about computing the price for 1 unit. Marginal cost, so that's 1 unit. You can't go less than 1 unit, right? There's no half a unit or quarter of a unit. There's just 1 unit is the smallest number of units you can have. And then the average one smooths everything out, and let's say over 100 of these it goes. So that's technically it. Good. So that takes care of the section 3.6, not 13. 13.6 is in Calculus 3. Got some ground to cover to that time. We're done with this. So next class we're going to do 13.7, 13.8. That's tomorrow. And we only have, I believe, 1 section to go, and we will be done. So we will be done with this chapter this week. So we're going to actually slow down a little bit, and next class we're going to have 1 lesson. Let's do just 1. Next class, which is, I believe, chain rule 13.7. 3.7. I'm still in Calculus 3 mode from my summer one. So 1 section next class, and then the lab time for you guys to catch up on labs. So we'll just do 3.7 tomorrow.
How many sections are we covering for this chapter?
I believe we are covering 9, or maybe 10. I'm checking it now. 10. 10. We're covering 10. We will be, oh no, wait, 11. 11, yeah, related rates. But regardless, we'll still be, we'll be in the half of the term on Thursday. The chapter 5 has only 5 sections. So this is going to be comfortable. And I believe chapter 4 has 9, right? So they're shorter than the first 2. So we'll be good.
So is the homework up?
I'm going to check what's happening with the homework now. Let's just stop this.